questions do you have for me? Either off the 8.5 homework or anything related to the test on tomorrow.
What are all we covering again?
So,
Everything.
almost everything, right? Inverse trig derivatives and integrals,
Okay.
hyperbolic trig derivatives and integrals, integration by parts, trig integrals, partial fractions, and trig sub.
So what like by section?
So
or
by
what sections are we
section-
not covering, I guess I should say.
It'll be easier to tell you which sections we are covering.
Oh, really?
Right?
Okay.
3.6, 5.8, 5.9, and then 8.2 through 8.5. Those are the sections to be studying for the test. Which is virtually everything we've
I
talked
was gonna
about
say,
so
like,
far
I
this
think those are the
semester, right?
sections we covered in lecture.
And good review would probably be to go back to the even book problems?
Even book problems, some of the review problems at the end of the chapters that correspond to it. Even book problems are definitely the better bet just because they don't have as many in the back of the book. I found that out because that's where I pull a lot of your WebAssign problems from, are the back of the book, or,
Okay.
or the back of the chapter. So,
See, I thought WebAssign put the problems in.
no, I picked the problems that go on WebAssign too. So,
Okay. Cool.
yeah, yes.
So if we're integrating with inverse trig, and we have something like pre-clear cut like 1 over x squared plus 4, do we still need to sub in a and u on the test, or can we just go straight to it?
You should at least write out what a and u are and the
Okay.
du.
Okay.
I'm going to say you definitely need to sub the u in, unless it's clearly that it's just x squared.
Okay.
So in other words, if your u is x, you don't have to do that because then of course du is just going to be dx, right?
Okay.
But if it's anything that's not just pure x squared,
Okay.
then you need to at least show me the u sub. All right.
You said 5, 6.
5.7, I think it is, or 5.8.
I think it's 5.8 and 5.9 were the ones we covered.
Yeah, 5.8 and 5.9. We're doing 5.6 today.
No, I thought
I thought we were doing 7.1.
We're doing 5.6 today.
Okay.
I changed my mind yesterday.
there's only 2 chapters that are on the test from 5.
Yeah, 2 sections from 5.
I thought there were 3 for some reason.
Just the inverse trig integrals and then hyperbolic derivatives and integrals is one section.
Okay.
Yeah.
Like that 5, 6 for some reason.
Nope. You don't want me to give you a test on
Yeah.
5.6 tomorrow when we're just going to start talking about it today, right?
No.
I was gonna say, please no.
You don't want that. All right. What else, y'all?
I think I'm curious about WebAssign, just like in general. So I forgot to plug in a square and it ended up, it was my third try, so it zeroed out. Can I do a new problem to try to get it, or is it just done?
You should be able, I believe, you could practice another version of it, but it's not going to do it for your grade
Dang. Okay.
because I only give you 3 chances on those problems.
Try again. I saw it get grayed out. And I was like,
Yeah. Nope. The way I've got it set up, it locks it after 3 attempts.
okay.
Yeah, I forgot C several times.
Yeah, that'll do it.
Yo.
That'll do it. That's why they usually give you a little hint on each question. Put plus C for constant or something. All right. Other questions? All right. I will put the solutions to those 3 extra problems, or 4 extra problems that I gave you on the 8.5 homework on the Moodle today so that you have it. And the partial fractions solutions for that practice are up now. I put them up this morning. All right. All right, so what we're going to talk about today is we're actually going to go back to something we talked about at the beginning of Calc 1, limits, everybody's favorite thing. Alright, so let's think about limits. Who remembers in Calc 1 what the very first thing you should always try with a limit is?
Plugging the X in.
Mm-hmm. Plug in your value that you're trying to approach, right? So direct substitution. And does direct substitution always work?
I'm guessing not.
No, right? Remember that was part of what we did in Calc 1, right? We sat there and said, okay, we tried direct substitution. If it works, great. But if not, you've got to do something else, right? And in Calc 1, that something else was either factoring and simplifying within the limit, right? Or rationalizing a numerator or denominator, or trying to rewrite with trig functions, right? Or let's see what else. Other stuff like that, right? So using basic algebraic techniques. So let's think about it. And so if we wanted to do a limit like this, so the limit is x goes to -1, 2x squared minus 2 over x plus 1. What would you have done in Calc 1?
Factored it.
So, well, before you even factored it, right? Remember, what's the first thing to try?
Direct substitution.
Direct substitution. So if I direct sub in here, -1, so that's going to be 2 times -1 squared minus 2 over -1 plus 1, right? So -1 squared is 1, 2 minus 2, that gave us 0 over 0. What did that usually clue to you in Calc 1? What did 0 over 0 tell you?
It's undetermined or indeterminate.
So it was in determinate form, which is what we're talking about today. But what did that mean then? Is this limit undefined?
Does it go to infinity?
The graph's not continuous. It,
Well, let's just think, okay, so let me rephrase that. What does 0 over 0 tell you about this limit usually?
As a whole? Well, as the first -1 doesn't it just go to infinity or negative infinity? Is that undetermined?
So pull out your graphing calculator. Look at the graph of this function around -1. What's going on?
it's normal.
Looks normal, right?
Yeah.
In other words, it looks continuous, even though of course we know it's not continuous, because if you plug -1 in, you're dividing by 0, right? So we know it's definitely not continuous. So what's that mean then? When you're graphing it on the graphing calculator, it looks continuous, but if you go to that table, it's going to say error, right? So if you go to second graph to get to your table, it should tell you error when you get to -1. So what's that mean then? What type of discontinuity do you have going on there?
Removable.
It's a removable discontinuity, right? Which means, what's true about this limit? Does the limit exist?
Yeah.
The limit exists, right? So remember, usually if you saw this 0 over 0 in Calc 1, it was a good chance that limit existed, right? And so then in Calc 1, what would we have done to find that limit? So you see 0, 0. Well, we know that's not a valid for the limit, right? But that then includes us in the limit exists. So what would you have done to find this limit then? No. Well, I mean, I'm not going to. You possibly could. But factor, right?
Yeah.
So pull 2 out of the numerator, and that's then x squared minus 1, right? And you know how to factor x squared minus 1. And then the x plus 1's canceled, right? Which then let you do this. So then you have limit as x approaches -1 of 2x minus 1. And you can direct sub into that, right? Because we've eliminated the problem with division by 0. And you got that limit being -4, right? Which hopefully matches with the graph which you just found with that limit. So, remember that's always going to be the first step, right? Direct sub, get 0 over 0, and then we tried some algebraic techniques, some different kind of algebraic techniques, right? Whether it be factoring and simplifying, rationalizing denominator and numerator, etc., right? So we have what we call this 0 over 0 form is an indeterminate form. So when direct substitution into a limit yields 0 over 0 or infinity over infinity. These are indeterminate forms. So these are the only two indeterminate forms you can have. 0 over 0 or infinity over infinity are the only two indeterminate forms. And the reason we call these indeterminate forms is they don't guarantee the limit exists, right? But they also don't guarantee what the or tell you what the value of the limit is if it does exist. So with this, that 0 over 0 didn't guarantee this limit existed, right? It was just a good chance if you had 0 over 0 that the limit did exist. And you could find it with some technique.
So you could possibly factor out, do it again, and you would still get 0. Like it's possible that the limit doesn't exist still.
It is still possible. If you see this, this does not guarantee that limit exists or not. It's just likely, if you see this, that for us the limit existed. Okay. At least in Calc 1. Okay. So let's look at another one. What about the limit as x goes to 0, e to the 2x minus 1 over x? So what's the first thing you should try here? Try direct sub, right? First and foremost, always try direct sub. Now you're going to notice I just put ds over my original direct sub, just indicating that I'm direct subbing here. That's just a habit. So if I direct sub in 0, right, that's e to the 2 times 0 minus 1 over 0. Well, right away, already a problem, right, because we're dividing by 0. And so then what's e to the 2 times 0? That's 1, right? So 1 minus 1 is 0 over 0. So we know 0 over 0 is a problem, right? So then, what would you do here? Can you use any of your algebraic techniques or trig techniques? Well, not trig, right, because there is no trig. Could you use any of your algebraic techniques from Calc 1 to try to find this limit? Can't factor, right? I would say you couldn't factor it.
Could you factor it just like you did x squared minus 1?
Yeah, so this is difference of squares, right, technically?
Yep.
So you could try factoring this as e to the x plus 1, e to the x minus 1, right? Make sure you keep your limit notation there. So remember, let's go back and review limit notation from Calc 1, right? When can you drop the limit notation? Whenever you actually found the limit, right? So at the point that you direct sub, right, that's when, so once you've found that limit, you're actually finding that limit by direct substitution, that's when you can drop that limit notation, right? In Calc 1, that might have got you a couple points off. Calc 2, I expect you to understand that limit notation and know how to use that limit notation, right? Which means, what do you think is going to happen if you drop the limit notation when you shouldn't?
You'll get points off.
How many points do you think you're going to get off?
All of us.
All the points. So if you don't use the proper limit notation at this point, because that should be still stuck in your brain from Calc 1, you lose all the points. It's wrong, regardless if all the work's right, because even then the work's not right if the notation's not right. So you've been forewarned, right? All right. So, does that help us though, factoring like this? Doesn't really help, right? It just kind of makes things uglier. So that doesn't help us. Could you do anything else that you remember from Calc 1 with that? Yeah, well, we don't have anything we can rationalize, right? That was the other big algebraic trick we did. So how would you find that limit?
Using a new rule, maybe? Hospital rule.
So, right now we know nothing about this limit other than you can't find it with algebraic techniques, right? So we need something else if we want to be able to find the limit exactly. Now remember, you can still graph this and approximate that limit, right? You could still build a table of values and approximate that limit by picking decimal points, getting closer and closer and closer to 0 on both sides. And if they agree, you have a good estimate of the limit. But if you want to find that limit exactly, we need something else. Because our algebraic rules don't always work. So that's where L'Hopital's rule comes in. Named after the French mathematician. And so that's why it sounds French. L'Hopital's rule. So the H is silent. And yes, there is the little thing that's usually going to be over the O if they're writing the name correctly. So what L'Hopital's rule tells us. So we have to make some assumptions. So f of x and g of x both have to be differentiable. So remember, what does it mean for something to be differentiable?
You can take the derivative of it.
You can take the derivative of it. The derivative exists, right? So you have to be able to take the derivative of your function f of x and g of x at least around the point containing some value a. So I'm not saying these functions have to be differentiable everywhere, but they have to be differentiable close to around some open interval containing a point A, and f of A has to equal g of A has to equal 0. So in other words, we have that indeterminate form 0 over 0. And you also have to assume that g prime of x is not equal to 0, except possibly at A itself. So you have to check these assumptions before you can use L'Hopital's rule. So the big things you have to check are both the numerator and denominator, or f of x and g of x, differentiable around our point A, and the you have 0 over 0. You have to check that before you can use L'Hopital's rule. If you meet these criteria, then the limit as x approaches a, f of x over g of x is equal to the limit as x approaches a, f prime of x over g prime of x. If this limit exists, right? Or if this limit is infinite, plus or negative infinity. So in other words, to find the limit of your rational expression that gave you that indeterminate form 0 over 0, you just have to differentiate the numerator, differentiate the denominator, and then take the limit of that new ratio, provided you met the criteria for L'Hopital's rule. And this also holds if f of x is different and g of x are differentiable for x near a, and you end up with, so you get the original criteria, f of x, g of x are both differentiable around a, and you get them equal to 0. So f of x and g of x can also be differentiable around a. And f of x, and the limit as x approaches a, f of x equals positive or negative infinity, and the limit as x approaches a, g of x equals positive or negative infinity. So in other words, you get 0 over 0 over here, right? So either way, the functions have to be differentiable around a. Here, you also have f of a equals g of a equals 0. In other words, this is your indeterminate form 0 over 0. Or, you still have the function differentiable around a, but not at a in this case. Or not necessarily at a. And now, of course, the function can't equal infinity, right? Because it's not a number. So instead, we say the limit as you're coming into a of the functions have to be either positive or negative infinity. So in other words, this is going to be the other indeterminate form, positive or negative infinity over positive negative infinity. So here I just wrote infinity over infinity. It could technically be positive or negative. It's just we commonly write that indeterminate form, we ignore the signs and just write infinity over infinity. Your book's going to write it as infinity over infinity if you look in your book. But it's technically positive or negative infinity over positive or negative infinity. The nice thing about this, these do not have to be the same infinity. It doesn't have to both be positive or both be negative. It just has to be something infinity over something infinity. And this rule is also valid provided you meet either of these two criteria. So not just for the limit as x approaches a, but also as x approaches infinity or negative infinity. So in other words, limits involving infinity. And one-sided limits. So in other words, you can use L'Hopital's rule on any type of limit So limit as x is approaching a number, limit as x is approaching infinity, limit as x approaches negative infinity, limit as x approaches a number from either the right or the left. You can use it on any type of limit, but you still have to meet these two criteria. Either the functions are both differentiable on an open interval containing a, and you have 0 over 0, or the functions are still differentiable around a, and you end up with the indeterminate form infinity over infinity. So you have to meet those criteria, but then you can use L'Hopital's rule. So if we go back to this limit, well, any questions about L'Hopital's rule first, before we actually try using L'Hopital's rule?
I think the questions and concerns will fix themselves as we go through examples and
They
examples.
should.
I do.
Yeah.
Well, not specifically L'Hopital. Isn't there more than just the two indeterminate forms?
Not technically. There are going to be other forms that I'll talk about in a minute
Okay.
that will lead to these forms.
Okay.
But you have to end up with one of these two forms for it to actually be considered the indeterminate form.
Okay.
But there are other forms that will get us to this form. And yes, your book, I hate this about your book does call them indeterminate forms. So if you're reading your book calls these other forms indeterminate forms. They're not indeterminate forms. The way L'Hopital's rule is actually written, the only two indeterminate forms are infinity over infinity or 0 over 0. All right. So let's go back to this one now. So we checked, we have the indeterminate form 0 over 0. That's the beauty of what direct sub gives you. Direct sub, you're checking that criteria. Yes, we met this piece. Or if you got infinity over infinity, yes, we have that piece by direct sub. Or direct sub is infinity over infinity, right? Because you're not obviously substituting in infinity, but you're taking that limit. So the other piece we have to check, are the numerator and denominator both differentiable? So if we consider each of these as functions separately, is the derivative of e to the 2x minus 1 valid around x equaling 0?
Yes.
Yes. Is the derivative of the function g of x equaling x valid around x equaling 0?
Yeah.
Yes. So that means we checked that box now. We checked that box. So here we have, so f of x equaling e to the 2x minus 1. That's differentiable around 0, right? And g of x equaling x is differentiable around x equaling 0. So we checked those boxes. We've already checked we have 0 over 0, so we're good. L'Hopital's rule applies. So that means if I want to find this limit now, the only thing I have to do is be able to take the derivative of the numerator and the derivative of the denominator. So what is the derivative of e to the 2x minus 1?
2e to the 2x.
Mm-hmm. And what's the derivative of g of x equaling x? 1, right? So that what L'Hopital's rule tells us is the limit as x goes to 0 of e to the 2x minus 1 over x is going to be the exact same as the limit as x goes to 0 of 2e to the 2x over 1. Yeah.
Do we have to write down that we're using L'Hopital's rule? Or how do we imply that?
So you might see me write it like that.
Okay.
In the past, I've been sort of stringent on that.
Okay.
You don't have to tell me that. So that's why I didn't write it now.
Okay.
I'm not going to be as stringent on that as I have been in the past. It's nice if you do write it, just to kind of indicate, okay, here's how I got from here to here.
Yeah.
It's my L'Hopital's rule, but you don't have to write that.
Yeah.
Just
Well,
like I'm not going to say you have to write the DS for direct sub now.
Right, okay, because I figured that would kind of cover it with the way that we made sure both are differential about
Yeah.
x equals 1 or
Yeah.
x equals 0.
And you don't actually, a lot of times you're not going to write this out. I'm writing it out now to be extremely explicit because it's the first time I'm doing it.
Okay.
But a lot of times it's just going to be something you're asking yourself.
Okay.
And who knows, it might be a question on test 2. What are the criteria you have to meet for L'Hopital's rule, or on a quiz or something?
Okay.
So you've got to know the criteria, and you should be mentally checking it. But I'm not going to be looking to see did you write out that this is differentiable around here and here.
Okay.
All right, everyone good? Yeah, Logan.
When you were determining that, and you were saying, you know, are they differentiable at A and such, like, you lost me. I mean,
All right.
and it was just like, yes. I was like, okay, what? Okay, we'll just roll with it, see what happens.
All
and
right,
still
so
got lost.
that, go back and look at section 3 point, I think it's 3.1 actually. It's either 3.1 or 3.2. Yep, 3.1, page 123 in your textbook talks about it. A lot of times, the easy way to find out if something's differentiable though, just ask yourself, is it continuous, right? Because remember, if it's continuous, if it's differentiable, it's definitely continuous.
Okay.
Vice versa is not usually true, but it narrows it down a lot. Because there are some continuous functions that are not differentiable everywhere. For example, the absolute value of x, right, is not differentiable at x equals 0. But you know that because you know it has that sharp corner there. So, but in general, most continuous functions are going to be differentiable. So in actuality, and we'll talk about this later on when we talk about polar curves, smooth functions are differentiable. So smoothness is that extra criteria to make it differentiable. If it's smooth, it's differentiable. And it just so happens the majority of the functions we're going to talk about and use this on are going to be smooth. So we don't deal a lot with stuff that's not smooth, like absolute value, in terms of differentiation.
And so, just so we said, you know, if it's continuous, it's probably differentiable. Continuous just means there's not a break.
Exactly. So no holes, no jumps, no vertical asymptotes.
Okay. Okay.
All right. And in actuality, to be differentiable, no holes, no jumps, no vertical asymptotes, and no sharp corners, or cusps is what we call them. All right. And if you know what you should know about e to the 2x minus 1, right? It's definitely continuous everywhere, but then it's also relatively smooth, just because it's an exponential function. So there's not going to be any sharp corners. The best example I can give you of a sharp corner, absolute value, because that is the definition of a sharp corner, right? The majority of these functions are going to be continuous and are going to be differentiable. So if we rewrite this limit, just to simplify that, since we know dividing by 1. And now, are we at a point we can do direct substitution? We should be, because we've taken care of division by 0, right? Which was what gave us that indeterminate form to begin with. So we plug in 0, we do our direct sub. And what is 2 times e to the 2 times 0? 2. That's 2. So that limit that we tried to find in the beginning, limit is x is approaching 0, e to the 2x minus 1 over x, is 2. Questions?
Making sure I knew exactly where you can drop the limit of x equals 0. So I do not want to be going through a test problem. Believe that.
Don't worry, you'll see it. You'll be doing a lot of these before the test, because we'll use limits again in the next section that we're going to do. All right, let's go back to this one that we found algebraically, right? Limit as x approaches negative 1, 2x squared minus 2 over x plus 1. So now we already know we did this limit using the algebraic techniques of Calc 1. So this is just overkill. But let's see if L'Hopital's rule works on it. So what do we need to check?
If f of x and g of x are differentiable.
So our f of x and g of x, so f of x being 2x squared minus 2, what type of function is that?
Quadratic.
quadratic, which is a special type of what? It is a parabola. The graph is a parabola, but what type of function is it?
Transcendental?
No.
That's like trig stuff.
That's your trigs, exponentials, logarithms, those kind of things. Inverse trigs. What is it? Starts with a P. It's a polynomial, right? So, polynomial. A nice thing about polynomials. Every single polynomial is differentiable everywhere. So if you see this is a polynomial, you can automatically say, yes, it's differentiable at around a. In this case, a being -1. So 2x squared minus 2 is differentiable there. So we check that box. How about x plus 1? Is it differentiable around x equaling -1?
Yes. Yeah.
Why?
Because it's a linear graph.
Which is a,
Continuous.
it is continuous, but it's also a,
Polynomial.
yes. So, might be a good quiz question or a good bonus quiz question. What's the definition of a polynomial?
I was gonna say polynomial. That's it.
Right? Maybe I'll make that a bonus on tomorrow's test. I haven't put it on I haven't printed the test yet, so I can still add that to the test. Yeah, Ryan?
Is it not linear?
It is linear. This is linear.
It's just a linear graph. Just
The denominator is linear. The rational function is not linear because of that hole. But your denominator is linear. And it just so happens all linear functions are also polynomials. Now, the reason this whole thing itself is not linear is because you can't do this canceling outside of the limit, right? Because it's not true that 2x squared over minus 2, but this is not true. That's not true, right? Because you've changed your domain here. You've changed what you can put in it. So that's definitely not true. But inside the limit, that's true. Well, the graph depends on if you're graphing it, what you're graphing it with. If you're looking at the graph of 2x minus 2 and the graph of 2x squared minus 2 over x plus 1 on your graphing calculator, it's going to look on the graphing calculator screen the exact same. But if you go into the table, you're going to see a value for 2x minus 2, and you won't see the value. You'll see error for the original function. The reason why it looks the same on the graphing calculator is just because of the size of the pixels that it has. It can only make it look so much like it. Yeah, James?
Now, couldn't we just say that the domain is the same for everything but that point?
You could write that out.
And
Yes.
And technically that would be mathematically correct then?
Yes.
Okay.
That would be fine.
That would all equal the same.
Yes, but I wouldn't write that out.
Right. I was just curious.
Yes, you can do that.
Okay.
All right, so back here we've checked the boxes. It's differentiable, numerator and denominator. We already checked with our direct sub that we have 0 over 0, so we're good. L'Hopital's rule applies. So this is equal to the limit as x approaches -1 of what?
Or 4x squared over.
What's the derivative of 2x squared minus 2?
4x.
4x over 1.
Can we direct sub now?
Yes.
Yes. Technically. And does that match what we got doing it algebraically? Questions? Yeah.
Is this going to go into what we learned in section 7? Is that why we're doing it now? Or?
Which section 7?
So,
It's actually going to go we're going to go back and do 8 point, I think it's 8.8 maybe. We're going to do improper integrals next. And you'll need it there, 8.8. And so you'll need L'Hopital's rule there. But it's also just a good trick to have. We just don't teach it. It's another application of differentiation. We just don't teach it in Calc 1 because you don't need it again until you get to improper integrals. Yes?
Do we need to write out that it's in indeterminate form? Like, do we need to do a direct substitution and show
You
zero?
do have to do this direct substitution because that should always be your first step anyways,
Okay.
is doing the direct substitution, right? So you're automatically going to be showing me that anyways when you do this. It just so happens, this happens to be that indeterminate form.
Okay.
So as long as you're showing me that direct substitution, you're fine. All right? Other questions? All right. Let's do another one. Now, before I say that, let me remind you of something to be careful of. L'Hopital's rule does not say that it's the limit of the derivative of this function, right? So do not use the quotient rule here. That's a big mistake I see people make sometimes. So if we go back to the one we just did, the limit of x approaches -1 of 2x squared minus 2 over x plus 1, right? It is not saying it's the limit of x approaches -1 of whatever the derivative of this whole thing is. So x plus 1 times 4x minus so it's not that, right? So don't do that, right? It's definitely not what L'Hopital's rule says, right? So be careful, don't use the quotient rule. So L'Hopital's rule does not say it's the derivative of f of x over g of x. It's the derivative of the numerator over the derivative of the denominator. Look at that. All right. Questions? Do another example. Come up with a read now. I'll call this 2. So what about this one? The limit is x is approaching 1 of natural log x over x minus 1.
Direct sub.
First thing to try is direct sub, right? So the natural log 1 over 1 minus 1. What is natural log of 1?
0.
That's 0. And 1 minus 1 is 0 all day long, right? So we've got that indeterminate form. So now, if you see that, well, I would still recommend trying some of the other algebraic techniques, see if they work. Now, I'll go ahead and tell you, since this is natural log, we don't have any algebraic techniques that help us with this, right? So that means we're probably going to have to try L'Hopital's rule. So let's check the criteria. Is f of x, so what's my f of x function here?
Natural log x.
Natural log x. Is natural log x differentiable around x equaling 1?
Yes.
Yes. And as long as you're coming in from the right, it is, right?
Yeah.
Because you can't differentiate from the left since
Yeah.
its domain is only from.
So it's not differentiable from the left, but it is from the right. So, okay. We can work with that. And what about 1 minus x minus 1? Is that differentiable?
Yes.
It's a polynomial.
It's a polynomial, right? Good. So that means L'Hopital's rule applies. So then, we can just go back here underneath our direct sub, right? And just say, okay, so the limit as x approaches 1 of natural log x over x minus 1, or you can even just carry the equals down again, does definitely equal to what? You tell me.
1 over x over 1.
Good. Make sure you keep that limit notation there, right? simplify that as limit as x approaches 1 over x. Can we direct sub down? What is it?
1 over 1.
It's just 1, right? So the limit as x approaches 1 of natural log x over x minus 1 is 1. Questions?
You said natural log of x, if you're coming in from the right, it's differentiable, but not from the left. I'm confused because I thought the boundary for natural log of x is 0, not 1. So don't you do it because you go from 0 to 1?
What's the range of natural log x?
Isn't it like everything but 0? Like, yeah. It's just weird because isn't there like technically like half? Like once it gets to 0, like if ever it gets to 0.
I misspoke.
What?
I misspoke. It is differentiable it's differentiable from the right up to 0. So it's differential on both sides around 1.
Okay.
It just so happens the y value is 0 here.
Yeah.
Because the domain of natural log x is the range of e to the x, since they're inverse functions, which is 0 to infinity, non-inclusive. Or inclusive, sorry. Yeah. So yeah, it's differentiable both sides around 1. Other questions? All right. We'll do a few more then. Or as many more as we can do in 4 minutes. Actually,
We can do one more.
we can probably get one more in. I don't think we'll get to
2 minutes.
I don't think we'll get it to the last example, but we'll get one more in. How about this one? Limit as x goes to infinity of e to the x over x squared. Now here, since this limit as x goes to infinity, right, we can't direct sub in infinity because infinity is not a number. But what do we know about if we take the limit as x goes to infinity of e to the x? Because this we can do, right? We can bring this limit into the fraction, right? What's the limit as x goes to infinity of e to the x?
Infinity.
That's infinity, right? And what's the limit as x goes to infinity of x squared? Infinity. So there's that indeterminate form, right? Infinity over infinity. So notice that's keeping consistent with how we wrote it over here, right? That the limit as x goes to infinity of the numerator is either positive or negative infinity. And the limit as x goes to infinity of the denominator is positive or negative infinity, right? So that's why I went ahead and wrote the limit inside here. Now in actuality, you can usually just skip this part, and normally for me, just write out this equals infinity over infinity. I'm just being extremely explicit in how I'm writing it. So e to the x, differentiable around as x goes to infinity?
Yes.
Yes.
Left side, yes.
And x squared as x goes towards infinity, differentiable?
Yes.
Yes. So we meet the criteria for L'Hopital's rule. So then this equals the limit as x goes to infinity of what?
E to the x over 2x.
E to the x over 2x. Now we've got a new limit. First thing you should always try is
Direct sub.
direct sub. What happens when I direct sub in infinity for e to the x?
Turns into infinity.
So it's approaching infinity, right? And as x approaches infinity, 2x approaches infinity. So once again, we've got that indeterminate form. So we check it again. So you can use L'Hopital's rule more than once. So we check it again. Is e to the x differentiable around as x goes to infinity?
Yes.
Yes. Is 2x differentiable as x goes to infinity?
Yes.
Yes. So we can do L'Hopital's rule again. So this is the limit as x goes to infinity of e to the x over what? 2. Now, what's that limit?
Infinity over
Well, you don't want to write infinity over 2, right? Because that's
Just-
not a number.
It's just infinity.
But infinity over 2, you should know, is just going to go to infinity, right? Right. Good.
And we don't need to say like we direct sub, it just
No,
equals
you need to say
infinity.
it's going to infinity. Good. All right, questions? All right, so let me write up the homework. Homework will be due sometime next week. I'm definitely not gonna make it due tomorrow since you got the test tomorrow. So section 5.6, and it's page 352 in your book. 7, 9, 12, 13, 15 through 39 odd, 43 through 53 odd, 79 and 81. And then you still got web assigned to use Sunday if you haven't already been working on it and turned it in. All right, but I wouldn't even say, don't even really start with it this night. I would rather you spend your time tonight studying for tomorrow's test. All right, questions? All right, see you tomorrow.